Welcome to our concluding discussion for week 6, which was all about reductions in the context of intractability. We saw the classes P, NP, NP-complete, and we saw the notion of NP hardness. We saw the concept of polynomial time reductions, which tie together seemingly unrelated problems. And reductions can be a lot of fun to think about and really interesting to work with because they provide a mechanism for making these deep connections between seemingly disparate problems. The more you work with reductions, the more amazed you will be at how seemingly dissimilar looking problems are actually intricately related. And of course, ultimately, all NP-complete problems are related by the fabric of reductions. But sometimes when you're actually working with a problem that you care about and you're not sure about its complexity, you probably want to find an NP-complete problem nearby to reduce from, something that looks or somehow feels related enough. It may not look similar superficially, but there's something in spirit that you can relate to. And to that end, it's useful to be familiar with a lot of NP-complete problems because having the right starting point can really give you an advantage. It's often turned out that there are problems that have been open in terms of people not knowing what its complexity is. We don't have polynomial time algorithms for it. We don't know if it's NP hard. We don't know if it's something worse or something in between. And finally, when an NP-completeness proof does come out, sometimes it's shockingly simple or elegant. It gets done in half a page. And often that's because the people who came up with the reduction were able to find the right problem to reduce from. And that can sometimes just make life so much easier. Of course, not all reductions are like that. Many of them are famously intricate and involved, and reductions can get pretty complicated. And sometimes that's what it takes to establish NP hardness or NP completeness, as the case may be. So there is a lot of variety when it comes to reductions, and it's a little bit unlike thinking about algorithms, because when you're coming up with algorithms, you're often going through your toolkit and you're throwing well-known paradigms or techniques at the problem, and some combination of it perhaps works out. This is not to say that designing algorithms is any less of a creative endeavor, but it's just that the flavor of how you think is a little bit different when it comes to reductions, where you're really trying to focus more on the process of mapping your problem to or from another one, right? So you're looking for similarities in the characters of the problems that you're working with. And of course, sometimes you are also using reductions to design algorithms, as we have discussed a few times by now. So your reduction muscle being well practiced is good for both establishing intractability as well as sometimes coming up with algorithms by simply reducing to other problems for which we already know that there are nice algorithms. So it works both ways and it's incredibly handy. But all of this is to really say that the more problems you encounter and the more problems you're aware of, perhaps the better your chances of being able to come up with interesting reductions. For all these problems, you don't necessarily need to know why they themselves are NP-complete. Just knowing that as a fact and being familiar with what the problem is like, what it involves, is already enough. So if you look at the course notes, you will find links to compendiums of NP-complete problems. So there is a classic book which lists several of them, and those are well known to be NP-complete for several decades now. And there are more recent references to online compendiums of problems that you can just go look up and browse through. Just as a starter, a very high-level classification of the kinds of problems that we have looked at, you could think of them as falling into the categories of packing, covering, or partitioning problems. So when you're trying to do a packing problem, you're trying to typically fit in multiple things without overlaps. So, for example, the independent set problem can be thought of as a very specialized kind of a packing problem. You're trying to pack vertices, but in a way that they don't touch each other through edges. Independent set also generalizes to something called scatter sets, where you are basically looking for vertices that are a certain distance apart from each other. So you want k vertices such that pairwise any pair of vertices has a distance of at least d between them. And you can see that independent set is a special case of the scatter set problem. And therefore, the scatter set problem is hard in general. And you can look this up if you want to find out more about it. But the other kind of packing problem that you would encounter is, for instance, something called set packing, where you're given, again, a family of sets over a universe U, and you're trying to see if you can collect a bunch of these sets, at least k of them, so that they're mutually non-overlapping or they're mutually disjoint. And sometimes you may want to relax this to say that, well, we allow only small overlaps, but we want them to be largely disjoint. So there are any number of variations on the set packing theme, and it turns out that most variations of set packing are quite hard, even in fairly restricted conditions. In terms of covering, we have seen problems like set cover, for instance, when we were doing dynamic programming. So with set cover, again, you're given a universe and a family, and you're trying to pick out sets from the family, which can be then used to form the universe. So you want a collection of at most k sets whose union gives you the universe. Notice that this is naturally a minimization problem, because if you had no constraint, then you could just pick all the sets that were there, and that would be the trivial solution. So similarly, we also have vertex cover, which is now a graph problem, and it's sort of the complement of the independent set problem. So a vertex cover is a subset of vertices, which is such that every edge has one of its endpoints in the vertex cover. So if you have a vertex cover, then every edge either goes across one endpoint in the vertex cover and one outside, or it sits fully inside the vertex cover. But what you're not allowed to have is an edge that sits completely outside the vertex cover. Then this set is not a vertex cover anymore. It really has to cover every edge. I realize that the name is a little bit confusing because it's a vertex cover, but it covers edges. I think the reason it's called vertex cover is to remind us that what you're looking at is a subset of vertices as opposed to a subset of edges, for instance. So observe that the complement of a vertex cover is naturally an independent set. So you could be looking for a smallest sized vertex cover or a largest sized independent set. They are in some sense equivalent, but as we will see later in this course, in terms of complexities, in certain settings, these two problems actually do have different complexities in terms of the kind of algorithms that we can come up for them. So now that we know independent set is hard, of course, because of what we just said, you can probably guess that vertex cover is hard as well, because finding a vertex cover of size at most k is basically the same as finding an independent set of size at least n minus k. So that's a two-line reduction connecting these two problems. And while they're related in this fashion, it turns out that under different algorithmic paradigms, which we are going to address as we start looking at how we cope with NP-completeness, these problems actually turn out to have slightly different characters. Now, we also have partitioning problems. One example of a partitioning problem that we saw would be the coloring problem, where we tried to partition a graph into independent sets. And as long as you're trying to come up with at least 3 paths, well, then that's going to be hard. We also saw the 3-dimensional matching problem, which you can think of as a partitioning problem in the sense that, well, it's trying to do both packing and covering, right? So we are trying to account for all the elements in the universe. So in that sense, we are trying to cover things. But at the same time, we are trying to make sure that all the sets that we use for this covering are mutually disjoint. So in that sense, it's also a packing problem. So combined, that would make sense for us to think of 3D matching as a partitioning problem, right? So you will find that many of the problems that you encounter probably have one of these flavors, which you can sort of start taking as a hint for wanting to reduce from perhaps one of these problems. And very often you might be dealing with problems in restrictive settings, and that can go one of two different ways. Sometimes a problem is hard even in a restrictive setting, right? So for instance, the coloring problem, you could ask if the coloring problem is easy if the graph is planar, if a graph can be drawn on a surface without any of the edges crossing. And in some sense, it does get easier because of a famous theorem which assures us that any such graph can be colored using at most 4 colors. So if you're happy with that, then, in some sense, your problem definitely just got solved. But if you want to know if your graph has a coloring with 3 colors as opposed to 4, then making that distinction turns out to be hard again, even if your graph has this very special structure. So sometimes problems continue to be intractable even if you restrict the input further, and that's useful when you want to show the hardness of other problems in other restrictive settings. So for instance, often you're dealing with geometric problems, so you want to say pack some cubes in a 3-dimensional space, or you want to pack rectangles that are not overlapping. So that's sort of an independent set kind of a problem, but you're asking the question of what you would call a geometric intersection graph. So every rectangle can be thought of as a vertex, and 2 vertices have an edge between them if and only if the rectangles that they're representing actually overlap. So you could think of that as the independent set problem, but on a restricted setting. And we have seen this before. We've seen independent set restricted to the intersection graph of intervals. That's what was actually happening in the dance classes problem. And we've also seen independent set restricted to trees. And in fact, there we even saw the weighted version of the problem, and we worked that out using some dynamic programming over the tree structure. And those are cases where restricting the problem makes it easier, but it turns out that if you start trying to find an independent collection of rectangles, mutually non-overlapping rectangles in the plane, then it actually turns out that it remains hard. But if you want to show such things, then often you want your source problem to also have some richness, which allows you to do a sort of a structured reduction that takes you to an instance of your problem in that restricted setting. So to that end, often what's very popular is variations of SAT. And if you look at the course notes, there's a link to a master's thesis, which actually documents a lot of SAT variants, which turn out to be hard in very restricted settings. So for example, not only is SAT hard when you restrict all the clauses to have 3 literals in them, it's also hard if you further restrict the frequency with which these literals appear across clauses. And there is a graph that you can naturally associate with a formula, which has, a vertex representing every clause and a vertex representing every literal. Well, there are many graphs that you can associate with a SAT formula, but this is one of the more standard ones where you just have edges based on incidences. So a literal is adjacent to all the clauses that it appears in. And it turns out that SAT is often hard even when this graph associated with the formula has some additional special structure. So those are the sorts of things that are discussed in this thesis that I just mentioned. And often these problems are great sources to start from if you're trying to work on some sort of a geometric problem and you're trying to show hardness for that. So basically the idea is to continue to increase your familiarity with a wide variety of problems that are known to be hard, because you never know when you're working with an unknown problem. You want to have sort of several triggers in your memory saying, this looks like this other problem that I've seen before. That's what reductions are all about. If you can locate a problem that has sufficiently same energy vibe, then you should be able to make that translation work out. So even though reductions can sometimes get fairly sort of technical and involved, at the heart of it is this intuition that, maybe these problems can be related in this fashion. And you start out with some sort of a blueprint, and often, just like we did with, for example, dynamic programming, what's usually going to happen is you come up with a construction. Chances are that the first time you try it, it's not going to work. So usually the forward direction will go through, because that's usually what you have in mind when you're coming up with the construction. But then typically you would have had some oversight or some little detail that will not work out in the reverse direction. So now you need to go back to the drawing board and enhance your construction further to fix the bugs. And it's really an iterative process. So when you're doing exercises around NP-completeness and reductions and so on, you don't get it the first time, then that's really nothing to worry about. It's very common that you have to do this back and forth circus before you actually nail it. And you will eventually nail it, and that's something that also is helped a lot by practice. So make sure to read up on some of the additional reductions that you can find in textbooks. I hope to add some more to the course notes and in supplementary videos in due course. So do check those out as and when they become available. So in the meantime, now we have reached some sort of an intermission at this course. We have seen a bunch of techniques for coming up with algorithms, which have mostly been polynomial time, with a few exceptions. And now we have seen this framework of intractability, which gives a lot of theoretical evidence for why for certain classes of problems we shouldn't be expecting to have, worst case efficient algorithms that are correct on all inputs. And now the glaring question in front of us is, how do we tackle these problems? Because we can't just stop at saying that we can't do anything. These problems still need to be solved in various real-world situations. And so the rest of the course is going to be about what is often referred to as coping strategies. So one way to cope is to say, well, maybe the problem is hard in general, but perhaps we should look at special classes of inputs, which is probably all that we care about in practice. So maybe wanting full coverage all the time for your algorithm to work on all inputs is too ambitious. So that's what happened with independent set when we said, well, let's look at independent set on trees or on interval graphs and things like that. So sometimes that's just all that you need, and that's very useful. So that's one way of coping. The other way is to say that, well, maybe you don't need an exact answer all the time. It's enough to be close enough to the exact answer. So that leads to this concept of approximation algorithms. And another approach is to say, well, we can't really afford any margins of error. We really need the absolute exact answer all the time. And then you have to sacrifice something when the problem is as hard as we have discussed this week. And there you typically sacrifice the running time. You say, well, we're going to get into the realm of exponential time algorithms. And there you try to make the exponential time as efficient as you possibly can. Those are some of the high level approaches to coping, and we are going to dig into each of these separately in the remaining weeks to come. So we're going to look at the approximation, randomization, and exact exponential algorithms, as well as a technique called parametrization that allows for a systematic study of special classes of inputs. And then, of course, we're also going to look at some heuristics that are extremely useful in the real world. So that's the roadmap for the rest of the course. I can't wait to discuss more with you. So thanks so much, as always, for your attention, and I'll see you back in week 7. Bye for now.